So I personally believe more on decarbonization than on defossilization. And there are a couple of reasons for that. Life is not possible without carbon. And what you see on the left-hand side, of course, that is human or plants, biomass. The carbon content over the whole planet in that three categories is about 30 to 50% of the dry mass. First, decarbonization and defossilization needs more renewable energy. We have heard that. At least in the steel industry, we have really a huge demand of more energy, more green energy. And the second statement is decarbonization and defossilization needs more cross-industrial and I have to add that cooperation with academia. Otherwise, we will not solve all the problems we have. The alternative is hydrogen. Substitute carbon by hydrogen and the byproduct of the steel will be the moisture or water. So this is an operation in Duisburg. We hopefully have our first direct reduction unit installed end of 26. Just to give you an overview how much more additional energy we need just for the decarbonization. We have a system which is changing from, let's say, 100% fossil-based to, in the future, 100% hydrogen-based. It is absolutely necessary that we had a lot of partners from chemical industry and also recycling industry, but also a lot of highly ranked scientific partners for CO2 emissions which are not point emissions. And for that reason, of course, direct air capture is essential. It's good to see that in that publications, scientists and guys from the industry really publish papers together.
So today I'm going to be talking about some of our long-duration storage modeling, specifically for the Western North American grid. And today I'll be focusing on one of the projects where we look at long-term planning in the US with the focus on long-duration storage. We still don't know in the United States how much duration and energy capacity, therefore power capacity, we will need for storage to support this growing demand and a zero emissions grid in the future. And in the case of these studies, we only look at one investment period in 2050. And for outputs, the classical outputs from a capacity expansion model, where we look at what will be the optimal investment by decade or for 2050 in our case study. So now let's get into some of these results of this study. If we look at the solar dominant regions, for example, here in the Southwest, in both scenarios, we see that we have a light pink dot that's representing 6 to 10 hours of duration, get optimally deployed to support solar power. So in the darker blue, that's the wind deployment. We see that we have a darker pink representing 10 to 20 hours of storage duration. So in this case, the different rows that we have in the table are representing individual scenarios that we were testing, where what we change across these scenarios is the energy storage cost that we assumed. We see that the energy capacity ranges substantially. We see that that number also ranges substantially, going from roughly 9 hours all the way to over 800 hours duration. We also observe that if some technology were to get to the lowest cost assumption, the $0.5 per kilowatt hour at the bottom, we would see a reduction in 75% of transmission needing to be deployed WEC-wide. Across all the mandates that we were testing, the one where we forced the 20 terawatt hour of duration being installed, that one results in the one that drastically reduces the variability of LMPs that we observe. So in the case of solar power, we see 6 to 10 hour duration optimally supporting solar. And in the case of wind-dominant regions in the WEC, we saw 10 to 20 hours of duration optimally supporting that region. As we move forward, regulation can have a huge impact, as we've been discussing. So in this case, I wanted to portray what would be the importance and the value of having storage mandates in the face of mitigating the volatility of prices of electricity in a zero-emissions grid.